Download this code from codegive.com, link in the description below. Apache Spark Architecture, an in-depth tutorial, Part 1. Apache Spark is a powerful open-source distributed computing system that provides an interface for programming entire clusters with implicit data parallelism and fault tolerance. In this tutorial, we'll explore the architecture of Spark in detail, discussing its core components, and how they interact with each other. Overview of Spark architecture. Apache Spark consists of two main components, the driver and the workers, executors. The architecture is designed to be highly scalable and efficient, allowing processing of large datasets across a cluster of computers. Key concepts. 1. Driver program. The driver is the main program that runs the Spark application. It is responsible for converting the user's program into tasks and scheduling them on the worker nodes. 2. Cluster manager. Spark can run on various cluster managers, like Yarn, Mesos, or Kubernetes, which handle resource allocation across the cluster. The cluster manager allocates resources, CPU, memory, to the driver and executors. 3. Workers/executors. The worker nodes run the tasks assigned by the driver. Each worker can run multiple executors, which are the processes responsible for executing the tasks and returning the results to the driver. 4. Task. A task is a single unit of work that is sent to an executor. Tasks are generated based on the transformations and actions performed on rows, resilient distributed datasets. 5. Resilient distributed dataset, RDD. Rows are the fundamental data structure of Spark. They are immutable collections of objects that can be partitioned across a cluster, allowing for parallel processing. 6. DAG, directed acyclic graph. When a Spark application is executed, Spark creates a DAG of stages and tasks. The DAG scheduler divides the tasks into stages based on the data dependencies. Spark execution flow. 1. Application submission. The user submits a Spark application to the cluster manager, which allocates resources for the driver. 2. Driver execution. The driver program initiates the application and creates roads, applies transformations, and defines actions. 3. Stage creation. Spark's optimizer creates stages based on data transformations and dependencies. Each stage is a set of tasks that can be executed in parallel. 4. Task scheduling. The driver schedules tasks to be executed on the worker nodes. 5. Execution. The workers execute the tasks and return the results back to the driver. 6. Result collection. The driver collects results from the workers and processes them as needed. Code example, a simple Spark application. Let's create a simple Spark application to illustrate how these components work together. We'll write a Python application using PySpark to process a dataset. Setting up PySpark. Before running the code, ensure you have PySpark installed. You can install it using pip. Sample code. Here's a simple Spark application that reads a text file, counts the number of occurrences of each word, and prints the results. Explanation of the code. Spark conf. This object is used to configure the Spark application. Here, we set the application name and specify that it should run locally with all available cores. Spark context, the entry point for any Spark application. It allows you to create roads and access the Spark cluster. Text file, this method reads a text file and creates an RDD. Transformations. Flat map, used to split each line into words, resulting in a new RDD. Map, converts each word into a tuple of word 1. Reduce by key, aggregates the counts for each word. Action, the collect operation retrieves the results from the RDD to the driver, where we print the word counts. Stopping the Spark context. It's important to stop the Spark context to free up resources. Conclusion. In this first part of the tutorial, we covered the basic architecture of Apache Spark, including its key components and how they work together during the execution of a Spark application. We also demonstrated a simple word count application using PySpark. In the next part, we will delve deeper into Spark's execution model, discuss optimization techniques, and explore more advanced features. Stay tuned for Part 2. Apache Spark Architecture, Part 1, Overview and Components. Apache Spark is a unified analytics engine for big data processing, with built-in modules for streaming, SQL, machine learning, and graph processing. It provides high-level APIs in Java, Scala, Python, and R, and an optimized engine that supports general execution graphs. Overview of Spark architecture. The architecture of Apache Spark can be broken down into several key components. 1. Driver program, the main program that runs the Spark application. It is responsible for converting a user's code into a directed acyclic graph, DAG, of tasks. 2. Cluster manager, manages resources across the cluster. Spark can run on various cluster managers including standalone, built-in, Apache Mesos, Hadoop Yarn. 3. Worker nodes, the machines in the cluster that execute the tasks assigned by the driver. 4. Executors, long-running JVM processes that run on worker nodes. Each executor is responsible for executing the tasks assigned to it and returning the results to the driver. 5. Tasks, the smallest unit of work in Spark. A task is a single operation on a partition of data. 6. Resilient distributed datasets, roads, the fundamental data structure of Spark. Roads are immutable and can be distributed across the cluster. 7. DAG scheduler, the component that transforms the logical execution plan, DAG, created by the driver into physical execution tasks. 8. Task scheduler, responsible for scheduling tasks to run on executors. Spark application flow. 1. A Spark application starts with a Spark context, which is the entry point for any Spark application. 2. The Spark context connects to a cluster manager and requests resources. 3. The driver program sends tasks to the executors, which run the code and return results to the driver. 4. The results can be collected back to the driver or saved to a distributed storage system. Code example, setting up a simple Spark application. This example will demonstrate how to set up a simple Spark application that reads a text file, processes it, and outputs the results. Prerequisites. Ensure that you have Apache Spark installed on your machine. You need to have Java and Scala installed as well. Sample code. Here's a simple Scala-based Spark application that counts the number of words in a text file. Explanation of the code. 1. Import libraries. We import the necessary Spark SQL libraries. 2. Create Spark session. A Spark session object is created to interact with Spark. The master is set to local * to run the application locally using all available cores. 3. Load data. The text file is loaded into an RDD using Spark context.txt file. 4. Data processing. Flat map splits each line into words. Map creates a tuple for each word with an initial count of 1. Reduce by key aggregates the counts by word. 5. Output. The results are collected to the driver and printed. 6. Stop Spark session. Finally, the Spark session is stopped. Conclusion. In this part of the tutorial, we explored the fundamental components of Spark architecture, including the driver program, cluster manager, worker nodes, and how tasks are scheduled. We also provided a simple example of a Spark application that counts words from a text file. In the next part, we will dive deeper into rows, data frames, and the Spark SQL module. Stay tuned.